This video is to help you understand Section 1.6 graphical transformations. First of all, transformations are functions that map real numbers to real numbers. So if a function is transformed, basically every point from the original function can be mapped onto a point in your new function. A rigid transformation will leave the size and shape of the graph unchanged, including horizontal translations, vertical translations, reflections, or any combination of those things. You should remember all of that from geometry class, or at least it should sound vaguely familiar. Non-rigid transformations will generally distort the shape of the graph, and transformations included in this are vertical and horizontal stretches and shrinks. We've talked about vertical and horizontal translations briefly in the past. What you should note is that with horizontal translations, any x value that you have in your function will have a number added or subtracted to it, or from it, excuse me, to move the function to the left or right. For vertical translations, you're adding or subtracting numbers to the entire function. Notice the difference. For a horizontal translation, each individual x value has a number added or subtracted from it, while in vertical translations, the entire function has a number added or subtracted from it. I'll now show you an example of this. If we take a basic function that you're familiar with, like say f of x equals x squared. You know what f of x equals x squared looks like. It's a parabola that looks something like this. Well, if we add, let's say 2 to every x value in that function, we end up with x plus 2 in parentheses squared. Think about where the 0 is on this. If I plugged in a -2 for x, I would get 0 for y. That helps you understand that when you add a number to the x, you actually shift to the left 2 units. If I were to take the original function and subtract 2 from the entire function, I would get x squared minus 2. That would shift the original function down 2 units. Take a look at this example. The original function, or one of your basic functions, f of x equals the absolute value of x, can be transformed to the graph of y equals absolute value of x minus 4. How would this graph be different? Or what would the change be? If you answered a vertical shift down 4 units, you would be correct. Here's what that shift would look like. In the this next example, you'll be finding equations for translations shown in a graph. The dotted red line in each of these graphs represents y equals x cubed. I would like you to write the equation that represents the blue graph. In example A, you should realize the graph has been shifted down 3 units. Write the equation for that graph. If you wrote y equals x cubed minus 3, you're correct. In example B, you can see the graph is shifted 2 units to the left. Write the equation for this new graph. If you wrote y equals x plus 2 in parentheses cubed, you're correct. And very similarly, in example C, you can see the graph is shifted to the right 3 units. Since it's shifted to the right, you're going to subtract, and your equation should look as follows. There are 3 reflections you need to be aware of. A reflection in the x-axis, which occurs when you multiply an entire function by -1. A reflection in the y-axis, which occurs when you replace every x value with a negative x. And a reflection through the origin, which occurs when you replace every x with a negative x and take the opposite of the function. The next note here is to be able to graph an absolute value composition. Whatever your function is, if you take the absolute value of the entire function, as shown here, what will result is the graph of the original function, but anything below the x-axis will be reflected above, and anything above the x-axis will just remain. For example, if we take f of x equals x cubed, our graph looks something like this, where if we take the graph f of x equals the absolute value of x cubed, we simply would take the original function, and anything below the x-axis would reflect in the x-axis, resulting in this case in a familiar graph. So the only part of the graph that you would have for the absolute value of x cubed would be this top portion. Similarly, if you take the absolute value of the x values within a function, as demonstrated here, what you will do is you will take anything to the left of the y-axis and reflect it in the y-axis, and anything to the right of the y-axis would remain on the right. Another way to translate your graphs would be to stretch and shrink them. If you have a horizontal stretch or shrink, what you're doing is you're taking each individual x value and dividing it by some c value. The graph will stretch if that c value is greater than 1, and there will be a horizontal shrink if that c value is less than 1. Basically what that's saying is you'll have a horizontal shrink if the x is being multiplied by a number, and you'll have a horizontal stretch if the x is being divided by a number. You could also have a vertical stretch or shrink. That occurs when the entire function is being multiplied by a number. You will have a vertical stretch when that number is greater than 1, and you'll have a vertical shrink when that number is less than 1. So right now I'll go through an example of finding equations for stretches and shrinks when I describe the transformation that I would like. The equation you're going to start with is y equals x cubed plus 3. What equation would you write if I want a vertical stretch by a factor of 4? Well, remember, if it's a vertical stretch, you're multiplying the entire function by a number. Since it's a factor of 4, you would take the entire function times 4. Be sure to distribute out, and shown below is your resulting function. For example B, I would like a horizontal shrink by a factor of 1/3. Remember, since it's horizontal, you are dealing with each individual x within the function. And since it's by a factor of 1/3, each x will be divided by 1/3, which really means each x is multiplied by 3. Don't forget, as you know, this cube can be distributed since the 3 and the x are being multiplied. That's how you get 27x cubed. In this next example, we're going to take that basic function, y equals x squared again, and do multiple things to it. First, I want you to take the x squared and create a horizontal shift 5 units to the left. Remember, when doing so, the horizontal shift requires you to do something to each individual x value. Going to the left means you're going to need to add 5. The next instruction is to have a vertical stretch by a factor of 3. Remember, when it's a vertical stretch, you're simply multiplying the entire function by that number. And then finally, a vertical translation 4 units up requires you to add 4 to the entire function. You multiply that out, combine your like terms, you end up with y equals 3x squared plus 30x plus 79. That's all that will be covered in this lesson. You can work together on the problems from the lesson. I expect everything to be attempted, and remember that you can use my binder to check answers.